Let's finish section 2.7, derivatives and rate of change. Remember, we learned the most important definition in Calculus 1, the limit definition of the derivative. Now remember, we're tending to focus on this definition. You really could use either one, but I'm always going to use the left-hand definition. Remember also the derivative of f at a, it's both the instantaneous rate of change, or instantaneous velocity, and the slope of the tangent line to the curve at that point. Remember, the tangent line is the limit of the secant line, so its slope is the limit of the secant line slope. And the instantaneous velocity is the limit of the average velocity. Right, that's the parallel going on. Right, so let's look at a couple of more examples, right? Find f prime of 7. Remember, that's the notation we use for the derivative of f at 7. So this is the limit as h approaches 0 of, right, that's f of 7 plus h minus f of 7 all over h. And when we plug that in, we're going to get 4 over 7 plus h minus 4 over 7 all over h. Now, this is one of these nasty repeated fraction examples. So before we go any further, I'm going to go ahead and write all over h as 1 over h, so that we have something not quite so bad. Right? That looks a lot nicer than this, I think. Anyway, how do we do this? Well, we need to add the fraction, so we need a common denominator. There's no nice way to do this, so what we're going to do is we're going to multiply this by 7 over 7, and we're going to multiply this by 7 plus h over 7 plus h. Let me write it out a little bit more here. All right, so we're going to get 4 over 7 plus h times 7 times 7. Let me just write it once. Minus 4 over 7, and then here we're going to do times 7 plus h over 7 plus h. Right? And so then anyway, when we do this, the whole point of a common denominator is that it's going to wind up giving us something a lot nicer, right? We can put it all over one common denominator, which is 7 times 7 plus h. And so we're going to get, what, 4 times 7, which is 28, minus 4 times 7 plus h. So we get that, right? Now remember, whenever you simplify, whether it's by common denominator, or multiplying by the conjugate, or factoring, whatever, you always want to simplify right afterwards. There's always some simplification to take place, right? Here, it's 28 minus 28 minus 4h, right? Pause the video if you don't see that. Right? So anyway, we have that. Those are going to cancel. And so now, what do we have? We've got this negative 4h. Notice that that's going to cancel with this h down there, right? Keep the negative 4, but get rid of the h's, right? I'll do that over here. Right, limit is h, that's an h, approaches 0 of 1 over h times negative 4h all over 7 times 7 plus h, right? The h's cancel. I said the h's cancel. And then we are left with, well, our answer, right? Just plug in 0 and you get negative 4/49. Okay. Another example. G of x equals the square root of x plus 3. Now note here that I say find the equation of the tangent line at the point 6, 9. That's a mistake, by the way. It should be 6, 3. So anyway, we do this. We're going to get, remember, the equation of the tangent line. We know the equation is going to be, the equation of a line we have the point. We need a point and a slope to make an equation of a line. We have the point, we need the slope. So we need the slope of our, maybe I'll do a double underline, of our tangent line at 6, 3. What is the slope? So we're going to find g prime of 6. And that's going to equal, now I'm just going to stop writing g of this, g of that, right? I'm just going to plug it in, right? We're going to get square root of 6 plus h plus 3 minus the square root of 6 plus 3 all over h, right? Right, and when we do this out, we're going to get the square root of 9 plus h minus the square root of 9, which is 3, all over h. And then remember, what do we do in this situation, right? We've got 0 over 0. We've got a square root minus a number. You guessed it. Multiply by the conjugate, right, over the conjugate, of course, because we can't change the value. Right, so this is going to wind up giving us 9 plus h minus 9 times h times, or divided by h times this nonsense. Remember, don't simplify that. You don't need to. These are going to cancel, and we're just left with an h over h. H over h. And then you cancel that and that, and you're left with a 1, and then you wind up getting 1/6, okay? So you might think, oh, we're done, right? No, we're not done. So the tangent line, right, it has slope 1/6, so it has equation, again, just underlining equation. Now, do you remember the equation of a line? It's going to be y minus y1 equals the slope times x minus x1. That's the point slope form of a line. We have to know that. Right? So we're going to get y minus 3 equals 1/6. That's why we had to do all that work to find the slope, times x minus 6, right? We had 6 and 3, right? That was given to us. We did all this work to find 1/6. Okay? Anyway, when you simplify this out, you get y minus 3 equals 1/6 x minus 1, and that gives us y equals 1/6 x plus 2. All right. Did that right? I think I did that right. Okay. So that's what we get. Make sure to answer the question, right? This example is particularly difficult and just time-consuming. Okay, this one takes a little bit of time. We'll do it. We'll do it, but it takes a little bit of time, right? Moving along in a straight line. This is the position function, right? Meters and seconds. Find the velocity when t equals 5, right? So another derivative question, right? So we're looking for f prime of 5. The annoying thing, right, is just that it's t to the negative 1 is 1 over t, right? So we're going to get this. It's going to be 1 over 5 plus h minus 5. Or sorry, not minus 5, minus 5 plus h, right? We're plugging in 5, right? This is the same as 1 over t, right? Okay? That's f of 5 plus h minus f of 5. Make sure to put parentheses around that. All over h, right? Now this is going to be, anytime we have a fraction, this is going to be another one of those problems where we're going to move the 1 over h out in front. We're going to have the negative 5 plus h, and then notice that the minus 5 right here, that's going to become plus 5. So they're going to cancel. So let's group stuff accordingly. We're going to have 1 over 5 plus h minus 1/5, and then minus 5 minus h plus 5. Okay, to be clear, this is the minus 5 minus h. This is the plus 5. Okay? So anyway, goes away. Right? Now, let's see what we get over here, right? Getting our 1 plus h, still keeping that out here. And then here, well, notice that we're going to have a fraction, right? We're going to have it's nothing nice, right? So we're going to have a common denominator, right? So if you do a common denominator for these guys, it's going to wind up being 5 minus 5 plus h all over 5 times 5 plus h. Right? And then don't forget about that hanging minus h. Okay? It's a little bit nastier than normal, right? Well, what's going on here? Do we see anything we can simplify? Hope you see it, right? We can cancel the 5s. This is going to wind up equaling, limit as h approaches 0, of 1 over h times negative h all over 5 times 5 plus h minus h. Okay? Now, here, you can think of this as minus h over 1. Why is that important? Well, because you can cancel both of these with the h down there, right? You cancel it with this guy and with that guy. So we wind up getting the limit as h approaches 0 of, I guess we don't need parentheses anymore, negative 1 over 5 times 5 plus h minus 1. Right? Now, this is, by the way, a little harder than something I'd ask you on a quiz or an exam. I guess we don't need the limit anymore, but I could ask you this on a homework, right? So this is negative 1 over 25th minus 1, and this winds up equaling negative 26 over 25. And they did give us units, right? So it's meters per second, right? Meters per second, okay? So again, tougher than something I'd ask on a quiz or an exam just because of all the arithmetic that's involved, right? We had to do fractions and fractions and fractions. But I do hope that you can understand this, okay? Now, here in example 4, we're going to go backwards. Normally, it's I give you the function, you give me the expression for the derivative, and then find it. Here, we're going to do the opposite. I've given you the derivative of a function at a point. I want you to find the function and find the point. The answers here are not unique. Your answer might be different from mine. But I'm going to do, I think, the most basic example, okay? So for A, f of x equals x to the 10th, and A equals 2. For a period there. For part B, this is a little tricky, right? But you need to notice that 2 equals the 4th root of 16. That's the trick. Right? Once you see that, we have f of x equals the 4th root of x. With A equaling 16. Okay? And then for the last one, this also is a little bit tricky, but you have to notice that since this is using the other definition of the derivative, right? But you might guess, since I guess you could say, 4 times 5 squared minus 3 times 5 equals 85, we have, I guess I can put it up here, right? F of x equals 4x squared minus 3x with A equaling 5. Okay, that's what we've got. Now we're moving on to section 2.8. We've been taking derivatives of functions at a point, right? find the instantaneous velocity at t equals 5. But what if I said, oh, shoot, I meant t equals 6. Actually, I need 7, 8, and 9. I actually need it in general. I don't want to have to do this process every time. So what we can do is we can actually think of the derivative function in and of itself, right? The derivative function, where instead of talking about a number like 5 or 6 or 7 or 8, we use x, okay? So for example, if f of x equals the square root of x plus 3, then find f prime of x. Not at x equals 6, just f prime of x. We're going to do the same exact thing that we've done before, right? F prime of x is going to equal the limit as h approaches 0. And I will write this one out, right? F of x plus h minus f of x all over h, right? I'm not putting in a number there, I'm putting in x. Okay? The problem-solving process is exactly the same as before. It's just a little more complicated looking. I don't think it's actually more complicated to do, but it's a little more complicated looking because we've got x's and h, right? We've got two different letters going on here, right? This is the square root of x plus 3 all over h, right? But we're doing exactly the same stuff. What did we do in the previous problem, right? When we did this, we multiplied by the conjugate. Here, we multiply by the conjugate, right? Same exact thing. Now, again, it looks a little nastier, right? We've got 2 radicals instead of 1. But it's the exact same stuff. The technique is the same. The simplification is the same, right? The radicals both go away. I guess it's plus 3, right? Minus parentheses x plus 3. All over in the bottom, as always, is nasty. I'm just going to get rid of those parentheses. Right, of course, we simplify, right? The x goes away, the 3 goes away, and we're just left with that h, right? And here we've got, I think I'm going to shift this over. I'm just running out of room here a little bit. Right, but anyway, what do we get? We get the limit as h approaches 0 of h, right? So just like before, h over h times all this junk. Right? And so we wind up getting 1 over the square root of x plus 3, right? Because h is evaluated at 0. All right, just to be crystal clear, maybe I'll plug in 0 in this case, right? X plus 0 plus 3 plus x plus 3. And that winds up being 1 over root x plus 3 plus root x plus 3. And that winds up being 1 over 2 root x plus 3. Okay? Now note if I said, okay, actually, it turns out we wanted to evaluate it at 6. Well, then we could say f prime of 6 equals 1 over 2 root 6 plus 3, and that winds up giving us 1/6. Just like we got here, right? But if I said, no, hold on a second, we actually want to do it for 7. And say, oh, okay, f prime of 7 equals 1 over 2 root 7 plus 3. 1 over 2 root 10, right? We didn't have to do any more work, right? So solving the general case can be desirable. And a lot of times, especially in Chapter 3, we're not going to necessarily evaluate the derivative at a point. We're just going to find the general derivative function, and then if there's a point of interest, we'll plug it in afterwards. Okay? So a couple of notes here. Taking the derivative of f is called, we can talk about just the derivative of f, right? Just the derivative function. We call that function f prime. Taking the derivative of f is called different. I'll write that a little bit neater. I'll try to write that a little bit nicer. Differentiation. if we differentiate y equals f of x, remember we had the limit as delta x, delta x approaches 0 of delta y over delta x. Remember how we had that? Well, when you do that, you write dy over dx. D means that delta is very small. So dy over if we're talking about y equals f of x, then dy over dx is another way of writing the derivative. Right? Dy over dx equals f prime of x. Okay, so if I say, given y equals 4x plus 2 quantity squared, then find dy over dx. All right, it's a lot of work, but let's do it. So we're going to get the limit as, as h approaches 0 of 4x plus h plus 2 squared minus 4x plus 2 squared all over h, right? Pause the video if you don't see how I got that, right? It's f of x plus h minus f of x, right? All over h. Right, now from here, as you might imagine, it's just a lot of multiplying out, right? We wind up getting, when you do it all out, it's 16x plus h quantity squared plus 16x plus h plus 4 minus, and then in parentheses here, 16x squared plus 16x plus 4 all over h, right? Now let's just do this out a little bit more. This is limit as h approaches 0 of 16 times the quantity x squared plus 2x plus h, right? And then when you multiply that all out, well, that's okay. I'll write it all out. This is going to be 16x plus 16h minus 16x squared minus 16x minus 4 all over h, right? Multiplying this all out one more time, just get rid of those parentheses. We get 16x squared plus 32x plus 16h plus 16x plus 16h minus 16x squared minus 16x minus 4 all over h. Now, remember, the goal of all of these derivative problems is always to cancel out the h on the bottom every single time. So what we hope is that all of the non-h terms in the top go away. And sure enough, they do. This cancels with that. Let's see. Oh, wait. Let's see. Oh, sorry. I had a little mistake up here. This shouldn't be 2x. This should be 2xh. That's 32xh. Sorry about that. That makes more sense, right? 2xh, right? Very important. Anyway, plus 16x minus 16x. Where did my plus 4 go? I think I forgot my plus 4, too. Forgot my plus 4. Forgot my plus 4 up here, because that's going to cancel with that. Right, just to be clear, my plus 4. I had forgotten my plus 4. Right, my bad. Anyway, we cancel all those, and I knew that we needed to cancel all those because those were all of our non-h terms. Anyway, we're left with this. Oh, that should be h squared. My apologies there. So this is plus 16h squared plus 16h all over h. I think you can see that we can now divide by h, the top and the bottom. And this will give us limit as h approaches 0, 32x plus 16h plus 16, right, all over 1. And that's just going to give us, maybe I'll do it down here, 32x plus 16. So that's our answer. That turns out to be our answer. Now, this took a lot of work. Maybe later on we'll learn a shortcut or two. one more quick lecture before we get into things. First, for review, find the derivative of the square root of 9 minus x. At this point, I want you to try it, okay? Try doing that one on your own. See what you get. A function f is differentiable if f prime of x exists. Or maybe I guess actually what we could say is a function is differentiable at x equals a if f prime of a exists. That might be a better way to say it. If f is differentiable at x equals c, for all c in an open interval, we don't talk about differentiability on closed intervals, then what we say is f is differentiable on the interval a to b. Again, we talk about differentiability only on open intervals. So then the question is, how can a function not be differentiable? Well, the answer is if the limit as h approaches 0 of f of a plus h minus f of a all over h does not exist. Now, how does that happen? Well, if a graph has any of the following shapes, we can have a situation where, first of all, if we just kind of, I'll just create a big axis, big set of axes right here. Maybe our function is discontinuous for some reason. Right? Maybe we have something weird like a cusp. Maybe we have a vertical tangent line at a point. Maybe we have a corner. Right? Maybe we have a corner. I'm trying to make that a corner. Right? Something like that. Yeah, so discontinuous, we've got that. Yeah, I think that's pretty much it. So here are problematic points, right? A, B, C, D, I'll call this S, and T. Okay, I think I got all those. In case you're wondering, an example would be like the absolute value of x. Here, this would be the cube root of x. This would be the cube root of x squared. And then these guys are just any discontinuous function, right? And the reason why this fails is because the tangent line at x equals a, or I guess I should say the tangent line to f of x at a is either not unique or it's vertical. Right here, the tangent line is like, here the tangent line looks like it's going here. Here the tangent line is going here, right? It's not unique. Here the tangent line is this guy, here it's that guy. Here the tangent line is vertical. Means it has a non-existent slope, right? So its slope is undefined. Right, so think of a function that's not differentiable. Most piecewise functions will do. You could use any of these guys. If it's a differentiable function A also continuous, the answer is yes. You can check the textbook for a little proof of that.